I'm now going to speak about how to model a bit more precisely the different organs of a plant. So it can be leaf, can be fruit, can be flowers, and this type of things. And for this, we start with a very simple aspect, which is you may want to create a leaf by using a polygon, and then displaying the polygon and filling the polygon in order to have a nice filled polygon representing whatever leaf. So it's very easy. To describe a polygon, you start by making a string that would correspond to the contour of the polygon using the turtle. So f plus etc., which makes a square. And then to create from this the polygon, you'd use these brackets here. And this will create a polygon for you, which is filled. That's it. So you just create your polygon with the turtle, and then you use brackets, and this will create the polygon for you. Okay? If you have concave polygons, like this shape here, you see that you just need, in order to fill the polygon, you just need to use the brackets, put all the code of your polygon, and then put a parameter of the brackets here that is called true, so that the polygon is the algorithm that is used to fill the polygon takes into account the concavity of the polygon. Otherwise, you can try with false or without argument, and it won't display a correctly filled polygon. Okay? So you can try. There is an example, number 7. Try this out, because it might be useful, because to create easily leaves, for instance, it's very simple, and you can create leaves with complex shapes like oak leaf. In this manner, you would have a polygon described by describing the contour, the winding contour of the leaf. So 1 minute on this. You can test a couple of examples that are given. Remove the true, add the true. There is a notion of dots in the example. You can see what it means, why there are dots. And please ask questions if you have any. Je touche plus.
Si t'as de l'argent, c'est à moi.
Comment ça va? Sorry, how are you?
Square 5 is not working.
Yes, because I saw this morning. I forgot something. Can you guess what?
True? No.
No, no. I forgot to declare square 5 as a module.
Oh, yeah.
So you need to declare square 5 as a module. If you don't do this, if you don't declare something that is a word, if you don't declare it as a word, LPy will assume that all the letters are as many modules, as many independent modules. So it will interpret the letters as modules, and then it doesn't find the module square 5.
But square 5 is not the same as square 2, because you get the border.
Yes. So the difference is that in square 5, there are capital F, you see?
Yeah.
So capital F is the cylinder with the default value, so it is interpreted by the turtle as something to display. This is why it is not the same. When I give in the square 1, 2, 3 the polygon, I don't display anything. So the small f is not displaying any cylinder. So this is why these examples are different. And when I give a capital F, I don't need to give the dots. If I give small f, I need to define the vertices of the polygon by as many dots as I wish. So with capital F, dots are optional, let's say. So in order to summarize this, if I want to draw a polygon like this, I will put a small f, because I don't want to draw the edge. So imagine that it's f of 1, let's say. Then I put a dot, then a plus something, and plus, yes, minus 30 to turn here. Then I put a f. So this was the dot was this vertex. No, I turn by 30. I do a f. I reach this point, and to say that this point is part of the polygon, I put a dot here, and so on. And if I have f, I don't need to put the dots. It's implicitly understood as after each f there is a dot.
And so, if I understand well, so when you use f, they're like kind of implicit dimensions. So if you don't put any values for f, it's one. Okay.
Yes, usually all the modules plus f
Like
minus, they have default values. If you don't put parameters, these are the default values that are used.
Okay. And
I'm not sure I understand the thing about light. Like you can't have light coming away and have on one side light and on the other one shadow. Like you either have both sides shadowed or lighting.
Yeah, it depends where is your light actually in the scene and where is the polygon according to the light. And it depends also on the model of light that is used in the system. So here, probably the light. Yes, I think we will need to double check this, but I think the answer is that the light, you don't have a face which is light and the other that is shadow. The face is always colored in the same color, but according to the position of the normal with respect to the light. You see what I mean? I will repeat this. I think this is, I will need to double check, but I think this is the answer. When I draw a polygon, the sense in which I turn, the sense, I will go the other way around. I draw a polygon, I turn in this sense, meaning that the normal will get out of the screen in my direction here. The normal to the surface. If the light is here, so closer to us, then this will cast light on the surface in the direction of the normal. So the surface will be enlightened, but because the sun is on the right side of the normal. But when you turn, it's not because of the algorithm that is used here is very primitive. The color that you have here doesn't depend on how you orient it just depends on the fact that the light is the normal is on the right side of the light. Is that correct? Is that clear? Okay, I will double check this with Frédéric. I'm not completely sure what I'm telling you now.
But because the light effect is only on the borders, not on the filling.
It should be on the filling.
But it's not like when you make the borders bigger so you can
Yes.
see it. You see.
Yes, but it should be on the filling as well, because here the color is dark because the
Normals are not defined, maybe.
normals are defined by the sense in which you are going through the contour of your shape. So it defines the normal. This sense, if you go counterclockwise or if you go clockwise, this defines the normal in either direction. And then normally, you should compute the light that is occurring here as a scalar product on the direction of the sun or the light and the direction of the normal. And no, I don't remember exactly the algorithm that is used. So maybe we need to double check this.
Is there a way to just remove the light effect and have?
Yes, you can. Yes, you can. In the window, in the graphic window, if you extend it, you have light somewhere. Yes, and then you see the shape like as if it was with ambient light or diffuse light. Okay. Other questions? Okay.
Yeah. Just
Yes.
in the code, I don't understand here. So to make the beautiful leaf here, so you've got the brackets to define your
Yeah.
shape. You make true because it's concave, okay? But why should you write at each line and produce and produce and produce?
Yes, because I just used the line was very long because there are many vertices in the.
Yeah.
So to cut the line into pieces,
You can.
I just yes.
Okay. Just his syntax.
It was just to have a reasonable size line. Okay, now we can move on to the sweep. So we already saw the sweep. So the sweep is a combination, as I said, of two curves and a width function that is controlling the combination of these two curves. So the surface, just to have a mathematical insight of what is behind, a point that depends on two parameters describes the surface in the 3D space. And if n and c are the curves, the surface is constructed by summing the first curve with the second curve, and this depends on two different parameters, and the second curve being scaled according to the width function. And to see how it goes, so you have the first curve here in yellow, you have the second curve, you have the width that will define how much along this curve I should stretch or compress the other curve, and then at each level I will apply the second curve according to the width that is indicated by the purple line. So this formula says exactly this. And when I have this, now I can make triangles or squares with this, and this provides the final output of this shape, which is a sweep, meaning that the green curve has been swept along the yellow curve and scaled by the other curve. Clear enough? Okay. So we use the sweep, as you have seen before, to draw a number of types of organs, and in particular the leaves, because you can change. Maybe you could try, for instance, to make an oak leaf just by putting a width that would So imagine that I have my nerve, would be like this. I have my section that would be, I don't know, like this. Okay. And then the width would be something that would go like this. And then the same on the other side. Well, almost the same. And then this would be Oak-Leaf, So this would be a way to make an Oak-Leaf with this type of system. It's very, actually, this just by combining two curves with a sort of possibility to module a bit the things is extremely powerful and makes it possible to create many types of organs. I think in the examples, I don't remember, I think I used this to create a couple. Is there an example that is called couple? Can you check this? So here, and is it made with sweep? Yes. So I think what I did is this. So to make a couple, I took yet a main nerve. Then I said that the section is a circle, and the circle should be dilated or stretched in any case, according to a law that starts small at the beginning, increases, then decreases, and then becomes like a tube in the end. And this, if I do this, I have something that is like this. In 3 dimensions. Well, I don't know why I did it in a twisted way, but it could be. And the couple in a plant is something that is like this. These are the ovaries, the over. This is the stele. And this is the heart of the flower. And then you would have the etamines on the side. And then you would have the petals. And then you would have the sepals. C'est ça, hein? Okay.
That's very interesting because from an evolutionary point of view, the idea is that the carpel is a modified leaf that has been that just rolled.
Exactly. And you see, we are doing exactly this.
So evolution just played with its function.
Yeah. So it's interesting because it's very flexible system where you can create open object, open surfaces, or you can create closed object like a vase or, okay? There is a slightly different object, but that gets its own properties. That is called the swungs. And the swungs, actually, just to give you a sort of main idea of how it works, the idea is to create a volumetric object by describing the different profiles that are on the object in different planes, by rotating the plane, okay? So it's basically like a surface of revolution, but where I would change every now and then the profile on which to rely, on which to lay. Okay, so this is typically you would have profile in this plane, this line, a profile in the different plane, which is this line, and what I want is that a surface that surround this object by getting as close as possible to each of the profile, and in a smooth manner. So there are algorithms to do this by using this NURBS type of surfaces. Each of the profile is a curve, which depends on the parameter u. You have capital K profile. Each profile is a small k. And then I create a P of u and v by combining this different profile and multiplying by this cosinus and sine, this cosine and sine of v. I can reconstruct the complete surface, and then mesh it so that it becomes a complete 3D surface. And this swang was implemented also in LPy and makes it possible to create this volumetric object that may represent a crown of a plant, but may represent many, many different things. For instance, one thing that we didn't do yet, Fabrice, is to, you know, the meristem is an object that is a bit like this. Okay? And we could, and this is in 3 dimensions. We have the small organs. You remember the picture that I saw yesterday? We could have the different profiles here. And from the microscope images, we could use this you could extract for each plane a profile and then construct a mesh using this swang system. And you see that it doesn't need to be symmetric. It doesn't need to be of a very regular type. You can, because you can use many types of profiles around, it will interpolate all the profiles and give you a surface that passes through all the profiles in a smooth manner. Okay, so instead of the example that I took here is how to create a pepper, and you see I used only 2 profiles here. So you can do complex surfaces. You don't need to have many surfaces. I used only 2 profiles, profile 0 and profile 1, which are the blue and the red. And you see, this was I created them with the graphical tool, and then I just I just say I have a profile list, which is a repetition of profile 0, profile 1, profile 0, profile 1, because there are 4 sections, 4 cappers in this object. So I duplicate this 4 times, this profile 0, profile 1. Then I associate a list of angles to explain in which azimuthal direction should each profile be interpreted. And then I call the swang with a profile list and an angle list. And then this creates this object. And this is in example, and then you have this. So this is example 9 and 9b, if you want to play with it. Okay? So could you play with it? Easy? So you see that you can create quite interesting shapes in a couple of lines of code, actually. So petal, fruits. I think I included also a banana example. You can try to make your own fruit, actually, or your own petal. You can take an orchid and try to simulate the petals of the orchid, which are sometimes quite involved, tricky. And I think you may find a way to assemble models in a way that you can reproduce the flower of an orchid. Okay, there are other models. I don't go through all of them. What is interesting is that these models have been made by I think something was missing. Beardbaum reference was missing here. So he proposed a way of measuring a plant in the field, because how do you get the crown of a plant? I mean, it's almost all the time quite impossible because the plant is big, and so one possibility that was proposed at that time in the year 90 was to measure a profile of the plant from the silhouette, measure a profile of the plant seen from below, and then combine these two. Yes, here. Combine these two by it's a bit of sweeping this profile scaled by the other profile. And there are other types of models that are included in LPy that you can use to construct different types of canopies. Now, texture mapping, just to because we were discussing this before. So, when we have a surface, the idea is to pass from a world of parameter, which is in 2D, to a world in 3D that corresponds to the points of the surface, and each coordinates in the UV parameter world would correspond to a point SUV according to a certain formula. the parametric surface. It could be a NURBS patch. It could be whatever parametric formula that you may want to have. Okay, so this is very very usual to have this type of description. The surface S, just so that you have this in mind clearly. The surface S would be a function of the two parameters and would be a vector composed of a function f1 of u and v, a second function of u and v, and a third function of u and v. So this is a vector. So for each uv, I will get a vector that will define my point in the 3D space, SUV. Okay? Now, it may be that I have a picture and I would like to map my picture on this surface. A picture is a square, basically. And as you see here, I have basically a square in 2D. And here I have something that is almost a square also. Can be a bit different than a square, but the fact that is important is that it is in 2D. So in order to map my image, so I have my image, and I want to map it on this surface. So instead of mapping directly on the surface, I will map my image on this. And then, since I have a correspondence of the point of the image to the point of the parameter space, then I will map the point of the image through the point of my parameter space through the 3D points. So it's very easy to do this. You just define how you map your image to the surface coordinates, and then automatically the transport will be made to the 3D object. Easy. By default, if the image is a square, if the surface parameter is a square, well, the square or rectangle, you map the corner on each other and assume that there is linear mapping. By default. It may be more complex. It is possible to have a more complex mapping in blue here, where there is non-linear mapping, and then you need to define a bit more precisely the way this mapping is defined. I don't enter into the details here, but it would be possible. And then what is amazing is that you can map the image on the surface in this way. Okay? So how this is done in LPy? Well, by simply, so this is the sweep primitive that we used before. And here, just before I draw the sweep primitive, I just set the color of the turtle, so actually this is the material of the turtle, to be the texture. So before I draw my surface, I set the color as the texture. So this is the set color or the semicolon 7. I loaded the image as a color before. So my color 7 is the texture. I load it here. I make a rotation because I want to apply my image in a certain position to my object. I scale my texture so that the image and the parameter space they correspond. It could be I want to have a repetition of my image and scale it up like a periodic tiling of my image on my picture. So I would use this. But if I don't want to do anything, I put 1 here, and then that's it. And then I call for my sweep function, and automatically, because the color is in the turtle is set to a texture, it will apply the texture to the object. Is that clear, at least for you, because you wanted to know how it works? Okay. And this is the way I put, let's say, on Arabidopsis leaves. I took picture of Arabidopsis leaves, and then I project this, and then it gives the impression that better impression in terms of computer graphics. Okay, and the final example And this might be for you, Fabrice, or David, maybe even better, because you wanted to know how you can curl leaf of Arabidopsis. So this would be the way. With time, the leaf would be produced laterally by the stem in a sort of straight way, like this or like this, and then with time, it would curl and change the shape. And how you would do this? Here, you need to put a new parameter in the leaf that I would use to compute curve. Instead of having one single curve, now I will have a set of curves. And I will, like for instance this. Let me take this. Okay, I would just put the nerve. The nerve would be straight in the beginning. Then I would fold a bit the nerve, fold a bit the nerve, fold a bit like this. Okay, even I can go in this way. Okay. So I will define curve 0, curve 1, curve 2, curve 3, curve 4, curve 5, curve 6. Okay. Actually, this is what I did here. I don't remember how many curves I used. And then I say, all this bunch, create me an object that is able to, given a time tau, that is able, what is this called? This curve function, get this curve function object. So the curve function object, it is able to take a time tau, and then to return a curve object as a C at the time tau. And then, so this curve object is provided by LPy. You just call it with a series of functions. Then, once you have this, you can call curve of t. And then if I know this t, I can compute the current nerve at time t, and then display it.
You have interpolation curve.
And actually, what is doing this? It is able to compute all the intermediate curves by interpolation, like this. And being given, so together with this set of curves, you give the time tau 1, the time tau 0, tau 1, tau 2, etc., up to tau 6, which are the times at which these curves should be observed. And then this interpolates at any time tau. This interpolates at any time tau in between the curves. Okay? And in this way, it's really easy to create an animation where the curves are, the fruits are growing, the leaves are folding or coiling. Okay? This function, I created this function by calling a specific primitive where I give the list of tau. I give this list of tau 0, tau 1, tau 2, plus the set of function. I didn't display it on the screen. You see? You find it?
Yeah.
Okay?
Just, yes, because in the code you say that tau should be between 0 and 1. So then I don't understand why you don't make tau like time, because it's a question of...
Yeah, because I usually in the programs that I make, I use tau when it should be normalized between 0 and 1, and t when this is more free.
Okay.
But it's my convention. What I say here is that I consider that the total lifespan of a leaf is 0 to 1. Okay? So now, if I have a real time what I'm going to do is to map the real time to 0, 1 without changing anything. So I will find the tau that will correspond to the real time unit. So I will transfer this first, and then I will be able to. Okay? And actually, this is a super generic way of computing and synchronizing all the events in the plant. It creates a sort of time model in the plant. Other questions? Yeah, okay.
Yeah, well, maybe, I don't know if I missed something, but if you, once you have an organ and you have this notion of aging, could you have like an internal clock? Or would you have to define it as a kind of a shared variable that is your T for this organ?
You can do whatever you want. Okay.
Maybe it's that.
Yes, yes. It's. I think this is an important question because it's how you model time in the system. So we can just review rapidly this. So first way of modeling time is maybe the most simple, is to have a global variable in your system. So what you would have is time equals 0 at the beginning of your program. Then you would have, let's say, production rule. That says A becomes, sorry. So A becomes produce if T equals a certain period, then produce, I don't know, B, a fruit. Else, produce A. IA, to say that there is an internode, IA. Okay. And I don't need to make an aging of A because the time is set outside.
Yeah.
But if I want to know, it won't work. Because for what reason?
But
Time must go on.
Yeah.
So in order to make this,
Maybe a root node that just doesn't change.
sorry?
Maybe some root node, that root module that doesn't change. It's just
Yes, you could do this in this way. But if you are in the mood of global variables, you would define in the start function. So there is, so this anticipates a bit what I wanted to say next. You will define in the start module the fact that T is incremented. Okay, there will be a module, sorry, not a module, a function that is called sorry, it's not the start of the program. It starts before each derivation. Okay, so before each derivation, I increment the time and then I go to the derivation itself. So there is a function that is a reserved name that is called star each, in which you can do whatever you want that will be executed before the start of the next derivation. Okay, so this we will see in a couple of minutes. And then this would be the way to use a global variable. But the problem with global variable is that they are global. And if you change something and you want to have local and etc., you may have side effects. And everybody sees this variable. Some people may change the variable behind your back. Yes, it's error prone. So in order to change this, the second option would be here to say, no, each module is counting its own time, which may be a sort of common time for everybody if you increment the time of everybody at each time by the same amount. Okay, so you have A of t, and then you would produce if t equals t, so it's exactly the same, then you produce a b, and else you would produce I followed by a of t plus delta t here. Okay, so now the time is local to each module, and there may be a problem. If all the modules do not increment the time in the same way, they will be at different times. So it's up to me, the user or the modeler, to increment everybody systematically with the same amount of time. I can do it differently, but this is called this is what we do in the aging. Instead of this, okay, the aging is a bit different because you can have the global time. Everybody will be incremented by the same amount of time, but the aging, everybody will be augmented by the same amount of age, but everybody won't start at the same moment in the global time. So the aging makes it possible to compute the actual age of the organ. So time is not the actual age. Time is time, like we are in 2022. Okay, but your age is independent of the actual time. It's the amount of time that you accumulated since you were born. Okay, so age is different, and then I could accumulate here the age, so with age plus delta t as well. But when this A was created, it may be in the course of the simulation. At the moment of this creation, this was the age of, the time of the parent, because the parent transferred the global time to the children without changing it, and an age which is 0. Because at the moment of the creation, the age of the new apex, of the bud, is 0 because he was just born now. So age and time is a bit different. And these are the two main ways to pass on the time value. So you need always to make the difference between the time and the age, and know whether you are speaking about the time or speaking about the age, because they are both referring to some time units. Okay? And I think that's it for the section.